Okay, this example is called a renewal chain, and the state space is going to be the natural numbers, so 0, 1, 2, 3, 4, and so on. What we're going to do is we're going to take this these numbers qx, right? So qx is defined for x, every natural number, and we're going to make sure that they sum to 1 and that each one is strictly greater than 0. So one thing you'll notice is that these numbers qx define a probability distribution on the natural numbers, right? So they're greater than 0 and they sum to 1, therefore they're between 0 and 1, and so that's a valid probability distribution. The next thing we're given are these one-step transition probabilities. So P0y is going to be Qy. That means from state 0, you move out to state any state y with probability Qy, which is positive. And then it says that to go down a state, meaning to go from any y plus 1 to 1, that happens with probability 1. So a good exercise is to kind of check that these are in fact well-defined one-step transition probabilities, right? Namely, each one is between 0 and 1, and the transition from any state out should sum to 1, right? And you can check that for the case of transitioning from state 0, summing up over y gives you 1, according to the way the q's are defined. And here, right, when the probability of transitioning from state 1 plus 1 is 1, there's nothing else to verify, right? That's a valid probability transition. It's a trivial one, meaning that it's prescribing sort of deterministic behavior no matter what happens when you're in a state of the form y plus 1, basically any number greater than or equal to 1. You will always move down a step to, from y plus 1 to y deterministically, no matter what happens, with probability 1, in other words. What my suggestion to what we're going to do is try to obviously compute the stationary distribution, and my suggestion always is to as soon as you've arrived or are given one-step transition probabilities, you should draw what's called a transition diagram. This will really kind of help you visualize the behavior of the chain and help a lot with various calculations. So what I've done here is just drawn out every single state, not every single one, right? I did it up to 4, and obviously the natural numbers go on forever, right? So the state space is infinite and it just goes and goes and goes. But what I've done here is sort of, I listed enough of the states to get a feel for what's happening, and you can see that from every number that's greater or equal to 1, we take a deterministic step down. So from 4 we go to 3, we go to 2, we go to 1, we go back to 0. And then from 0, right, there are all these possible transitions to any state. So we start from 0, we can go back to 0 using Q0. We can go to state 1 with probability Q1. We go to state 2 with probability Q2, and so on and so forth, right? And this goes out to, to an infinite number of states, right? So it's an interesting example to give you a sense about why it's called the renewal chain. You can use it in a lot of different modeling scenarios, but the classic one given is the lifetime of a light bulb. So the idea is that you buy a light bulb and you're at state 0, and there's going to be some probability that you bought a crappy light bulb, and with some other probability you bought a very long-lasting light bulb. And so the Q's are those probabilities, and so right at time 0 we skip ahead to some lifetime, and that's going to be, for example, how many days this light bulb is going to last before it burns out. And so, for example, we took a random transition to, say 100, and then the chain steps from from 100 to 99 to 98 to 97 all the way back, right? And at the end, when it returns to 0, that marks the point at which the light bulb is extinguished, and you have to go to the store and get a new one, right? And so that one lasted 100 days, you get a new one, you're at state 0 again, you get thrown way out there to some other state, maybe like 86 or something, and then the 80, then that number decreases all the way down to 0, and so it takes 86 days for the light bulb to go out, and so on and so forth. And I encourage you to kind of come up with your own examples. This is really applicable anywhere where you're sort of determining how long something will last. So here we're all about computing stationary distributions, and I mentioned in kind of the theory part, lecture 3, where there was this global balance and local balance conditions, and the local balance condition, which is right here, right, for all x, y, this was hold. If you can get those to work, then they're much easier to deal with than are the global balance counterparts. However, there's sometimes a very easy way. Often there's a very easy way to tell when local balance just has no chance of holding, and this has to do with our next lecture on reversibility of processes. And let me give you a little bit of a preview why I would say there's not even a point trying to verify something like this. To check on potential reversibility of a chain, which is kind of coincides with this local balance definition. A reversible chain looks the same whether it's moving forward in time or backwards in time. So pretend you're looking at this chain and you're recording kind of with maybe some video equipment. You're recording what's happening, and you can very easily detect when it's moving forward in time. Right, it will make a big skip, and then it will deterministically go click, taking sort of decrementing by 1 on each step all the way back to the beginning. Then it'll go way out there again to some qx, and then from x it will come back slowly, one step by step back. Picture kind of video, making a video of this and then playing it backwards. What happens when you play this video in reverse? Well, it kind of does the exact opposite. It starts from step 0, and then it will go back to 1 it'll kind of rewind itself to 1, to state 2, to state 3, to state 4, up to some x, and all of a sudden it'll throw itself back to 0. And that looks, you can very easily tell one from the other, right? One, goes out and then comes back slowly, whereas this one kind of swims out very slowly and then, gets thrown back. So, the two movies look very, very different. The example of sort of the movie playing backwards it reminds one of kind of, say you're kind of swimming out into the ocean and a wave kind of crashes you back to the shore, which is the state 0, right? And so when you're watching this movie backwards, you're going 1, 2, 3, 4, and then at some point a wave comes and just washes you back to 0, right? And that looks very, very different than first jumping all the way out to some very positive state and then slowly moving backwards. So based on that, and we'll see this kind of how this plays out in theory in the next lecture, I would immediately disqualify these local balance conditions because they are equivalent to this notion of reversibility. However, we haven't covered that yet, so let me just try to show you mathematically why it's not going to be possible to find a pi satisfying these equations. So let's, how would I do it? Well, it seems like state 0 is a nice one to try, and you just start writing, what it means, like start translating this for a particular state, right? And so I put pi 0 here. This one is going to be then pi 0 x, for example, right? Well, here I put y, so maybe I can switch this to y, right? So pi 0. Then from 0 to y, what is the probability of that? That's qy. And what is the other side of it? The other side is coming back from y, right? Starting from y, going y back to 0. So I'll just replace the x with a y again. Y here, and a y here. And that is going to be equal to 0. So why is that? At least for the case y greater than 1, right, what's the transition probability from a state y, which is greater than 1, say 4, immediately to 0? Well, there's no way to get to 0 in 1 step. You can get it in 4 steps, but these are 1-step transition probabilities. So this number right here is 0. And so what's my conclusion? Well, each qy is greater than 0, strictly greater than 0, and this side is 0. So I immediately get pi 0 is equal to 0. So immediately you can kind of see that there's something suspicious going on. Like why would, in the long run, the probability of being in state 0 be 0? That just doesn't seem right, right? We kind of played around with this chain, how it looks, and that just seems strange. It's not necessarily, it's not a proof that the stationary distribution does not exist. We're about to come to that, but at this point it's not a proof, but this right here you already start being suspicious. It looks like the state Q0 will be visited pretty often, because every time you come out, you always return to it. But no solid proof yet, so let's move on to the next state. Let's, instead of taking y greater than 1 here, let's take it to be 1, right? Let's check for the local balance between the pair of states 0 and 1, right? 0 and 1. So 0 times, starting from 0, the probability of going to 0 to 1 is Q1, so this corresponds to this side of the equation, right? And what's on that side? On that side should be pi 1 times the probability of going from 1 to 0, which is actually 1. So this equation holds. Q1 is greater than 0, pi 0 is 0, therefore pi 1 is 0. So now we have two states that are 0. And you can actually keep going and conclude that if this is to be satisfied, it would imply that every pi x is equal to 0. So how would I do that? I would start with a state. Let's say I'm going to take x to be greater than or equal to 1. I'm going to start with pi x plus 1 and argue that that's equal to pi x plus 1 p x plus 1 x. Why is that? That's by definition of these p's here, right? These transition probabilities from state x plus 1 to x, right, decrementing the count, are always 1, so these two things are equal. And if local balance holds, then I must put here pi x, probability of going from x to x plus 1, right? The pair of states that I'm applying this with are x plus 1 and x, right? And so these would be the local balance equations. And what do I get here? What's the probability when x is greater than 1 to go from x to x plus 1, meaning a transition that way? Well, they're all 0, right? We're going from state x, right? That's at least 1 up, and all of these transitions are missing, right? That's why this diagram is so useful. So this is equal to 0, right? Because this guy is always equal to 0 when x is greater or equal to 1. And so, you at that point you've concluded that pi 0 is 0, concluded that pi 1 is 0, and now any pi x plus 1, or just in general pi x, is 0. And so now we have that if these equations are to hold, they imply that pi is 0 everywhere. Why is that not a valid stationary distribution? Well, that's because its entries don't sum to 1. And so this is an example of detailed balance not working, and we'll see in the next lecture that it doesn't work because of this fundamental property of reversibility or irreversibility. In the next clip, let's actually compute out this stationary distribution using global balance.